Full screen. So you guys see my presentation?
Yes, we can see it. So yes, Yashar, please go ahead.
So hello, everyone. This presentation revolves around a taxonomy-centric classification of moving objects. I'm a PhD student, a second-year PhD student at the Memorial University of Newfoundland under the supervision of Dr. Suarez, who happens to be the chair of this session. So without further ado, let me dive in. The classification of moving objects has a wide range of applications, since there exist all kinds of moving objects in different fields, such as cars and buses, tourists, ships, hurricanes, human hands, animals, asteroids, and much more. Now, let's see what sort of data we are looking at when working with moving objects. The raw data in classification of moving objects is trajectory. A trajectory is a sequence of movements in time as depicted in the figure. Now, classification of trajectories per se is inefficient. As a workaround, researchers and practitioners employ descriptors. A descriptor basically is a scalar which summarizes a trajectory from a certain aspect. Now, when a descriptor is not dependent on the time component of the trajectory, we call it a spatial descriptor. Otherwise, we would call it a spatial-temporal descriptor. Now, with descriptors defined as such, we can reframe the classification of moving objects in a more conventional manner. Now, suppose we have n trajectories belonging to either cars or buses. So the response value here is either car or bus. Now with n such instances, along with n predictors, we will end up with the familiar data frame for a classification task. Now let's see why spatial-temporal taxonomy really matters. Now, based on the source of a trajectory, spatial descriptors may not be available or just be poorly available. Same thing can be said regarding the spatial-temporal descriptors. For example, in this first case, the source of the trajectory is a trace of a trajectory in an image. As a result, with the temporal component missing here, spatial-temporal descriptors are not available. In the second case, the surveillance camera is the source of the trajectory, where the angle of the camera may obscure the geometric properties of the trajectory and hence compromise the spatial descriptors. Therefore, the predictive performance along the spatial and spatial-temporal line is quite important. The taxonomy actually is important from another perspective as well. Spatial and spatial-temporal descriptors as a whole have a coherent, distinctive, and intuitive definition. For example, we have a clear understanding of geometric properties as a subset of spatial descriptors having to do with the shape of the trajectory, and kinematic having to do with the motion, meaning that the taxonomy may actually help with the characterization of moving objects. Now, inspired by the last two slides, one can formulate two research questions in particular. Now, as a proof of concept, I limited the focus to geometric and kinematic descriptors as a well-established subsets of spatial and spatial-temporal descriptors. The questions are, how did geometric and kinematic descriptors compare in their predictive performance? And second, to what extent they can characterize the difference between moving objects. The current studies focus solely on the predictive performance on a single classification problem and on a handful of descriptors. And second, they do not investigate movement characterization based on spatial and spatial-temporal taxonomy. And therefore, I started looking into the problem. The trajectories I've been working on so far belong to ship traffic. In the Pacific in July 2019, I included the most common ship types as the labels. and selected a decent size and balanced set of most popular descriptors for simplicity. Now, with that in mind, I can now give you a glimpse into the early results. Now, I have looked into all the possible classification problems on 6 classes, summing up to 57 classification problems. In this graph, the y-axis denotes prediction error of 3 models per problem: geometric model, kinematic model, and benchmark, consisting of both geometric and kinematic models. The x-axis represent the problems, which are increasingly sorted and labeled according to the prediction error produced by the benchmarks. Now, I have highlighted 3 problems for simplicity. In problem number 56, which is the classification problem consisting of all the 6 classes, the geometric and kinematic descriptors perform worse on their own. In problem number 2, which is the binary classification between sailing boats and tanker ships, the predictive performance of kinematic descriptors approach the benchmark. This would imply that sailing boat and tanker ships differ in motion rather than the shape of their trajectories. This is vice versa for problem number 5, where we see for the classification between cargo and passenger ships, the character difference can be ascribed to the shape of the trajectories. Now, next, we will try to further characterize the difference between the movement of cargo and passenger ships in problem number 5. Now, this graph is called a partial dependence plot. In a nutshell, the graph shows how the probability of classification changes across 2 of the most important descriptors in this problem. The barcodes portray distribution of instances for each reading of the descriptors. The geometric descriptors here are the length of the trajectory and the first signature of the distance geometry, which basically measures the straightness of a trajectory. These 2 descriptors, in fact, very well discriminate between these 2 types of ships. The graph implies that the more tortuous the trajectory, the lower the probability it belongs to a cargo ship, except when the trajectory is very, very short. With that said, we can now sum up the set of very early findings. Now, we have put forward an estimate of predictive power loss when either spatial or spatial-temporal predictors are not available. And second, the feasibility investigation of movement characterization inspired by the taxonomy. Now, with that said, one may expand on these early results in different directions. For example, one can diversify the data sets by resorting to various disciplines and explore spatial or spatial-temporal descriptors other than the geometric and kinematic ones. One can refine the taxonomy, perhaps in a hierarchical manner, which can lead to a more accurate characterization of moving objects based on predictive performance. And finally, one may look into the similarity bonds induced by the taxonomy for future selection. Now, with that said, I'd be happy to answer any questions if you guys have any.
All right, we probably have time for one quick question. Go ahead.
Go for it, Amika.
What? No.
I said fire it.
you are the star here. Come on. Go ahead, Renata.
Yeah, I'm sorry. I have so many questions, but I'm really enjoying this session. You mentioned 3 different ship types. 2 of them you mentioned they have this similar shape. The trajectory have similar shape. And you mentioned 2 others that did not have similar shapes, and the 2 others that have similar shape, but the motion may differ. What is the motion?
Oh, the motion. All right. So the motion, the kinematic, it's basically a term from physics, right? So the motion is, so let me, perhaps I can, all right. So under spatial temporal descriptors, you would see some of the classical example of motion, like acceleration and speed. So motion is any descriptor which would have any physical attribute which have time at its core. So you need time to be able to calculate it. That is I would call it motion. Now, a descriptor which actually gauges the motion, I would call a spatial temporal descriptor. I don't know if I could answer your question.
Right. So the fishing boat, I don't remember if a fishing boat and the tanker, they may travel the same speed or have similar acceleration or whatever. But the cargo and the tanker, they may go in different acceleration, but have similar shape in the trajectory. Is that what you're saying?
Yeah, that's correct. I mean, for example, this example, a cargo and passenger ship. So the model here is a geometrical model. So all the attributes are pure geometric. Now, this attribute can finely discriminate between these two types of ships. The other attributes which have to do with the motion may also be able to discriminate these two types of ships. So, for example, in this, just give me a moment. All right. So in this graph, if both the green dots and the orange dot actually approach the benchmark, which happened to be the purple, then we know that both geometric and kinematic models perform very well. Of course, this is not the case all the time. So the fabric of this picture is very, very mixed and varied.
Yeah, no, thank you. I understand now.
Sure.
Thank you very much. Yes.
Sure.
All right. Thank you very much,